Hello everybody, hope you guys are doing well. So continuing on our journey, today we would be trying to understand uh, different like today we will be trying to before going on ahead, we will try to understand what um, what threads is. Like we will be understanding threads and uh, interprocess. Like what are the we will try to under first we will because threads is how Swift is going to work, right? So we'll understand threads versus process, right? We will try to understand these things and then we will go on from there. Before we go ahead, just let me check if the so we will try to understand how threads and processes are related to each other, and we will see like what's the difference between them and when should we and like what happens in each case. So now threads, now process is basic. So let's start with process, right? So we said process is basically process is an instance of a program which is being executed, right? So process is an instance of program which is being executed. Now there is a process. There is a so all our apps will be written in some sort of language, right? Then language can be anything. It can be C, Java, C++, or anything, right? So for example, this is our so like the program will be stored in our either it would be in our external hard drive, either we would have and we would be storing it in our local disk. So either it would be an external hard drive, or either it will be it will not be a read only memory, like it will not be a RAM. So it can be any type of ROM in which the memory is being retained, right? So in RAM the memory is not retained. As soon as you turn off the power, everything is lost. So then if this is our C program, right? So to run such a C program, let's not take and so see something has a GCC some and compilation stages, right? Okay, let's see. Now inside the memory. So what is going to happen is now. So to execute this or to get the output, these all have to be moved to the RAM, right? And remember, RAM is a hardware. So RAM, I can say RAM is a hardware. Now this hardware will only understand one and zeros, right? But then when we write our C language, so C language stored here would be written in a high level language, right? High level language, which is similar to English, like it would is similar to which is similar to English, right? But then the RAM will have to the RAM will need something like 1 and 0, right? Oh sorry, when we move it inside the RAM, it should be 1 and 0. Now why we need to move is because CPU can access only the RAM, right? So to execute the program, you need some sort of CPU execution time, right? So until unless you get a CPU execution time, you won't be able to uh, you will be able to run the program. Now what happens when you have a language like C? Okay, so first, so now ultimately goal is our machine language. So ultimately we need a machine language format here. So we need a machine language. But then in our so where we are writing program in a high level. So we are writing program in high level. So now we need to convert this high level to a machine level, right? So that is the job. So some processing needs to be done, right? So generally we use a C compiler and an interpreter, right, for this purpose. So C C compiler and interpreter is what we are going to use, right? The job of the C is basically, okay, first, so now execution in C language occurs in two stages. So first is we check whether the English syntax we written does it follow the language. So then we do a compilation. So we do a compilation to check if we are following the language rules. If we are following language rules. Now once that is done, then what we do is then we convert this. So when this is done, then we get our executable, right? So actually it's going to happen in only one step itself. So then after this compilation step is what we do something called as interpretation, or we generate the executable, right? So we try to interpret or generate the executor. This executor is nothing but 1 and 0 language. The moment this language is generated, so what our OS does is, now it needs to have a CPU time, right? So what it will do is the OS will create a process for this, right? So then in the this will be my OS scheduling cycle. So in this scheduling cycle, what I'm going to do is this is my CPU scheduling. So in my CPU scheduling, I'm going to schedule the process, right? So when we say we want to schedule the processes, we want to give it the CPU time. So what we will do is, like, there will be many processes that we are going to wait in this block, right? So what we need, so let's have a, so this is our CPU and then this is our RAM, right? The moment, so now this, the job of the scheduling algorithm is to define when are we going to get CPU time. So here is my scheduling algorithm job from the RAM. So in RAM we basically have the process which is running, right? And then, so what does a process contain? I mean, what all elements will it contain? So basically a process gets its own process block. So we have a process block that is being assigned here. So this is my process block. So first thing basically that I have is I have my process ID. Then basically I have something called as memory units, right? Because we need to store all the data in the, so we also need the data and everything which is stored in the local variables, right? So we will have a unit for that as well. So we have local memory storage units here. Now there are, so in a program we can have two types of memory, right? So either it could be a stack or either it could be a heap. So after converting, this is the final stage, like when we have the 1 and 0 and then when we want to give it CPU time, right? So then we need to generate this process control block, or so this is nothing but called as PCB or my process control block. So hence we said that process is basically so if you see the definition, a process is an instance of program which is currently being executed. So we say it's an instance of a program which is currently under execution, means which has CPU time, right? So whenever that which is ready to get the CPU time, depending upon the scheduling algorithm, or depending upon the priority of the program, the scheduler will work, and then based on that, uh, the scheduler is going to schedule and execute the program. Now let's see what do we mean by when we say threads, right? Now, now threads is basically okay. Now let's come back to something called as threads, right? So what do we say threads? Now when we say a thread is basically the smallest unit of execution within a process. That means we are saying a thread is a um, smallest unit of process being executed. Now, what we are by when we say it is the smallest unit of a process being executed, we'll try to understand this. Now, because of the event of something called as multi-threading, what we so our goal is basically to make sure that the CPU time is not wasted. So our goal is to make sure CPU time CPU is not idle. So this is our main goal that we want to achieve, right? I have to open a new page, it seems. Let's say view. No, not open. I didn't get. Okay. Yeah. So CPU. How to have a new page here? That is something. Mm, let's go to. I'm not sure. Okay. Let's. No. Yeah, we our main goal. Mm, okay. So our main goal is. How should I hide this? This is headache. That's Okay. Now it should. Now, because of this, what we want is we don't want our CPU to be idle, right? Our main goal is to make sure that our CPU is our main goal is basically to make sure that our CPU is not idle and we are consuming the CPU, right? Because CPU is a very valuable process, and then always there is a fight uh, to which for the process to happen, right? But then now with the advent in technology, we said we need to not only do we not we need the CPU to be able, we also want to have concurrency being achieved, right? So we also want concurrency to work. That means we are capable of having multiple things running at a similar time, even though when we have a single process, right? Now concurrency was possible when we had multiple processes, right? So if you have two processes, you can have two things running at the same time in two different processes. But then the thing is, like with each processor, now see, the problem with the multi processing is these are on two separate chips, right? So data transfer traveling will take some time. So we don't want that has to happen. We don't want even that time to be wasted. So instead we came up with a concept called as, let's have something called as multi-threading, right? So let's have a concept called as multi-threading. Now this became possible because now we don't have one single CPU, right? Instead, in all of a single chip, we have multiple CPUs being working around. So we have, instead of a single chip, we have multiple chip being working around. Let's select and then so we don't want our program to stop, right? Instead we want that, let that program being. So these are all CPU ALU thing, right? So you have CPU and ALU. Now to achieve concurrency, either what we can do is we can we can achieve concurrency at the process level. That is nothing but called as multitasking, right? So multitasking is basically, switching the process after a fixed interval of time. So let P1 run for like 10 milliseconds, then I have P2 for another 10, then I have P3 for another 10. So basically what we are doing, we are forcefully making the switch in the process. By this we are making that there is no process level starvation, right? But then what we further came, right? What we said is, instead of having a single process, like a single process being an entire program, we divided that progress into multiple small fragments, right? So basically what we did is, so this is one big process. So instead of running this entirely once, because every time we make the switch, right? Every time we switch from process P1 to process P2, we are going to waste a lot of time, right? By wasting time, what I'm trying to say is, like every time, so the moment we make a switch, we need to store a lot of things, right? For example, we need to store at how much the process was executed, what was the state of the memory at that time, and like how much is the process left yet to be executed, and from when should we start the execution. So this is a very good information, right? Very like it's a very heavy information. Instead, what we want to do is we want this process to finish as soon as possible. So we want this P1 to get consumed as fast as possible, right? So what we do is, instead of having a one single program being running, we divide the process into different threads. So like we say, let this program be divided into three threads. So I have a thread one, I have a thread two running. Now by this, what we are doing is, this is my process P1. So what we are doing is, now instead of this the one entire process coming and sitting here, what now we are going to do is like have the thread sit here. So we am having thread one, thread two, and thread three. So now this will do is, instead of like waiting and then switching, um, it might so happen that the program might so short that the CPU ALU thing might consume it in one go as well. CPU ALU might consume it in one go instead of making it sit. So this is nothing but what we say, right? So we say we have a big process, and in that process we divide the process into different sections so that they can run independently and parallelly. But then now what happens is, now we need to know how this what we say when two threads need to communicate, what is going to happen here. So that is something that we need to understand, right? So in on similar lines, what like so to sum it up, what we can say is, um no, process multitasking is good, right? Multitasking is making sure that all applications that we are running, sometimes run in the background, right? So you need to make sure that even that gets a significant amount of CPU time. You don't want any process to starve it. So what we do here is, basically we divide, instead of having a one single process, we make multiple processes. So we have process P1. Okay, instead of having one single process, we have multiple process being present here. So this is process P1. So okay, so this is, so to sum it up, this is my CPU, right? And this is suppose my process P1, and this is my process P2. Now these processes are going to have multiple threads running in them. So it can be thread 1, thread 2, and then thread 3. Multiple number of them. Depends upon how we define the smallest execution thing possible, right? This is T1, T2, T3, T4, and T5. So basically, again, that is nothing but how multi-threading is going to work, right? So multi-threading is basically the smallest unit possible in our process, right? But the moment we say about processes, we say like inherently we are mentioning that a process may have multiple threads, right? So basically, now what we need to know is how to synchronize the processes. Now this is something. Now what if uh, so I have two applications running, and what if the data is being transferred between these? So say for example, in process P1, my thread 1 needs something that is present in process P2 and thread 3. So how is this going to happen? What are the problems that are going to occur? So is multi-threading a good option? Yes, multi-threading is a good option, but then there are other engines design as well, uh, which can further and like which can overcome the drawbacks that. So multi-threading is not a very good thing, because synchronization between processes, that is going to be a pain. So let's see what happens. Now synchronization too. Okay, first let's see what the issue is. Now a system typically now we are going to study process synchronization. So let's see process synchronization. Now, a system typically consists of several, multiple, or even hundreds of threads running either concurrently or in parallel. Now, threads often share user data. Meanwhile, the OS continuously updates various data structures to support multiple threads. This condition occurs when the access to a shared data is not controlled, possibly resulting in corrupt data values. The process synchronization involves using tools that control access to shared data to avoid various conditions. The tools must be carefully used as so there are certain drawbacks when we or certain problem that we are going to solve. Okay. Now, a cooperating process is a one that can be affected by the other process execution in the system. Okay, so now that means so when we say when we have two dependent processes, they are called as cooperating process. In other words, they are going to cooperate with each other. Right? So then we have something called as cooperating processes. Now, this cooperating process is the one that can affect or be affected by other processes. Now, cooperating can directly either they can to cooperate. The English meaning of cooperate is let's say the English meaning of cooperate is basically to work together in sync. Maybe so. Cooperation basically means to work together, right? So see, this is that co means to and operate is to work. So this is to work and this is to right together. So basically, we are going to say together working process or okay. Now, concurrent okay to be okay. Cooperating process can either directly share a logical space and or be allowed to share data only through shared memory or message passing. Now, concurrent access to shared data may result in data inconsistency. We will see various mechanisms to ensure that we are going to ensure that more of this synchronization is going to occur. Now, let's see. Now, there are going to be critical problems, right, that are going to occur. So, the first, okay, when we became the first, now the first drawback that we occurs is, okay, let's see a code. For example, we have a code and let's consider, okay. Now, we have already stated that process can exist concurrently or in parallel. Now, section introduced the role of process scheduling and described how the CPU scheduler might rapidly. So that is nothing but multitasking. This means that one process might partially complete execution before the other process is scheduled. In fact, a process may be interrupted at any point and the processing may be assigned to the execute instruction of the other process. Additionally, section introduced parallel execution in which two instruction streams representing different execute simultaneously on separate processing cores. So basically, our goal is to understand concurrency. We understood what is multi-processing, multitasking. We are now in concurrency. Now, in this chapter, we will explain how concurrent or parallel execution can contribute to issues involving the integrity. Now, let's consider an example. Okay, now we are going to deal the problems with cooperation. So, what problems do we go through? Problems when two processes cooperate. So when I have two processes so let's see, let's consider an example how this happens. In chapter 3 we developed a model of a system consisting of cooperating sequential processes or all threads are all running synchronously and possibly sharing data. Now we have listed this model with the producer consumer, which is the representative paradigm of many operating. Specifically, we describe how a bounded buffer can be used to enable process. Now there is a famous problem that happens, right? So let's see the processes. The producer consumer problem. So let's see producer consumer. Now let's see what happens when we have the producer consumer problem. Now it's the producer of, okay, so first thing that we are going to study is, what we are going to see is producer consumer. let's yeah. Now it's a synchronization problem where a producer generates and data and puts it in a buffer. A consumer takes the data out of the buffer and processes it, but they both can't use the buffer at the same time in a conflicting way. Let's see a real life example. What is going to happen? Now, for example, okay, why is it okay? For example, when you go in a hotel, a chef is going to make the food, right? So the chef cooks, chef is cooking, chef cooks food. So this is my chef, and then we have a waiter that picks up meals from the counter. So then we have the waiter, right? The job of the waiter or a server is basically to okay. So this is my waiter. This is going to serve. Now a counter has, and then he's going by serving. What we mean is going to the waiter is going to come pick up the meals and put the meals on the table, right? So this is on the table, and then so suppose we already have multiple products being placed here, right? So now the waiter can praise the product only if this table is empty, right? Now the chef can put more meals if it's full. The waiter can't serve. It's if the waiter cannot put the meal here if the table is empty, right? So what should happen is the chef should ideally coordinate with the waiter, right? So the chef and so basically the chef can work cook the so there is no limitation, right? The chef can cook and keep the meal ready, but until and unless there is space on the table, the waiter can only place the meals if there is some sort of space available, right? If there is some space available on the table, right? So until and unless there is no space, the even if the chef can cook, the waiter won't be able to place it, right? So ideally, what should happen is the chef and waiter should coordinate with each other, right? The chef should talk to the waiter, and it should be vice versa. I mean, this should be a two-way coordination, right? Only then is the so if there is a perfect coordination here, if there is a perfect coordination, only then we can if there is a perfect coordination, only then we can do the only then it will work properly, right? And the meal will only be then placed on the table if these both are working in coordination, right? So this is nothing but we need to so basically the issue is that they need to be synchronized, right? So basically this two-way communication is nothing but what we say that uh, they need basically to be synchronized with each other. So until and unless there is a synchronization, we will not be able to achieve that thing, right? Now okay, let's see how the same problem in our code. So let's see. Now we develop a model of a system consisting of cooperating processes, right? That means two processes are going to work together. Now we illustrated with this model with the producer which are representative paradigm. Okay, now okay, let's see. Now I have a producer code and I have a consumer code. Now let's see in terms of code usage what is going to happen. So I have a producer code. So this is my producer. So I say this is while true. and then this is basically so here is when I'm going to okay, this is my buffer size. Now, so buffer in is equal to next produce. Now in now, okay, let's see. So I have a producer function, and then I have, so both the producer and the consumer are going to write to a common buffer. Okay, so then okay, so if I have a buffer, okay, so this is my buffer size. This buffer is basically array, right? Then I'm going to say at the index of the array. Okay, this is where I'm going to put my next produce thing, right? Okay, and then I'm going to do, this is for increasing the count, right? So this is a very good, so when, so for example, instead of doing I plus plus, I'm doing this modulus thing, and then I'm going to do, so by what he's saying, if I'm overfilling, if my, suppose if my buffer size is 4 and count is 4, right, then I'll be eradicating this, like I will not be entering in this loop. Okay, I'll be skipping this part. I see. So I'll be skipping this part. And then now the code for even the code will be the, for the consumer will be the same thing, right? Oh, so, oh no, no, wait, I guess so. This is some other loop. So if I've exceeded the count, then I'm not going to, okay, this is some different loop. Let's get rid of this. Yeah, okay, if this is, then I'm not do nothing is what, just wait for an empty spot to be available, right? If I get an empty spot, then put the next item in the buffer, increase the size, and then increase the count. This is at the producer end, so I'm here. Basically, this is the chef, right? The chef is going to prepare the meals and keep. Now we'll see, like, so this is basically, okay, we'll see when the process, when it is going to break, like when is the code going to break. So even for the waiter side, I'll be having an infinite loop, right? And then when there is no space available for me to put, then I'm going to, so my, when my count is 0, I don't have anything, I'm just going to relax. Else what I'm going to do is, I'm going to do next consumed is buffer out, and then I'm going to have a modulus being run over here. So this is, and then I'm going to do, so why I'm doing count minus mass, because this is the table, right? So as soon as I put in your item, that much space is going to get occupied, and that many less number of items can be put, right? So as soon as I have the items placed here, this is going to be finished. Now I only have less number of spaces available, right? Now this is ideal. This working is very ideal, right? This is how it should be working, right? But then there is going to be a problem, right? The problem. So where and how will the problem occur? What if these two processes are executing concurrently? Now we'll see what is going to happen. So I have process P1. This is my process P1. Now I have both of them. So like I have allotted threads to them. So for yeah, this is how my diagram is, right? So this is my thread 3.1. I say this is thread 3.1 that is working on, and then I say this is thread 3 T2 which is working on, right? Now these two processes are working together, right? So because I have multi-core, so this is my multi-core architecture. So if it's a multi-core, then the process execution will occur uh, simultaneously, right? So now what could happen is, unless and until they both know, but unless and until there is a synchronization thing. So here, because it is going to happen, here we are saying that it is working one after the other, right? So we are not assuming. So in the above thing, okay, we are waiting. This is one after the other code. This is no, there is no concurrence, no concurrency happening here. The moment we have concurrency, we need to communicate between each other, right? So because if there is no communication happens, then this might increase the count, although there might be no space available here. We don't want that to happen, right? So for that reason itself, because each, so the moment we say CPU plus ALU, right, what is going to happen is each is going, so each CPU will contain its own set of, ultimately the data will be stored in registers, right? So each will have its own set of registers. If we were reading from a common location, then that wouldn't be a significant problem, right? The problem is they are going to be stored in two different registers, so that is where the problem is going to happen. So now we need something called as synchronization. Because of this importance, hence now we will arrive. So this is basically an issue, right? So we need to solve this issue, right? So this is nothing but um, uh, this is why, because each, if each CPU had like a common register, then I don't think so that would be a problem. But then in multiple core processors, um, in multi-core processors we have each core has its own CPU and ALU. Yes, that is where the issue lies. That is where our problem is going to occur. Hence we need process. Hence we need something to be synchronized. Now this is the drawback, right? This is this is what is hence we need a synchronization. But the problem is the way registers are designed is how, right? So the job, so we need a very fast access to the memory, right? Like, what happened? Did something? Yeah, yeah, we need the um, and yeah. So the problem is, even if we have, so the problem is CPUs are not designed to be sharing things, right? But sharing things will ultimately lead to a slow speed. These registers, the onboard registers, are designed to be very fast because CPU is very fast. So hence, if that is going to happen, then we are going to reduce CPU speed if we share. So hence, because of having that different thing, different each CPU ALU having its own. Okay. Yeah, because these registers should be extremely fast, right? They shouldn't wait for anything. So that is the reason. If you have a shared location, then the speed is going to reduce. But CPU needs a very fast access. So we are ultimately reducing this CPU speed, which is a very bad option, right? So hence hence each ALU or each CPU core gets its own set of registers. So, but yeah, like the synchronization in issue can be solved if you have but different registers, but then they are not made that way just because the way how CPUs are designed is different, right? Multi-core architectures or how multiple cores design is different. But then we would still be stuck in the race around condition. We'll see that, like what is going to happen. So yeah, that's all for this session. I'll see you guys in the next one. Till that time, take care. Bye bye.